Looks like we can get started. Welcome back, everyone. Thanks for making it in today. Today we're in section 2.7, absolute value equations. And my goal is to get to section 2.7, part 2, the absolute value inequalities. That's going to finally round out all the inequality work we've been doing, starting in section 2.5, 2.6, looping back to 2.7, part 2. Then with the remaining time that we have, we'll look into section 3.1. We may finish this one, and 3.2 is just here just in case we have extra time. I'm not too sure if we'll actually get into that section, but sometimes I like to have a little bit extra in the notes just in case. We also have our very first quiz posted, quiz number 1. So that's the natural thing to talk about next. But any questions from you folks so far? Okay, well, let's open up our first quiz. These are going to be posted on a weekly basis, and you'll usually see them just on Thursday. What it's intended to be is just give you one overall question as kind of a wrap up of the content we did before. I'm not going to ask loads of questions on this one because there's already plenty of homework to do up here in the Newton system as well. So here's what the quiz 1 looks like. Click on just the link here in the Canvas page, and all it is a PDF file. It says it's due September 11th. These due dates are always going to be 1 week away from when they are signed. Open this, and here's the quiz. So pretty much it's just a basic quiz number 1, due date, and just the 2 problems that you see right here. This one's on solving a compound inequality, and this one's solving the absolute value equation. We'll do one of these again just to start out class once we get into the notes. So these are what the quizzes look like. Sorry, full disclosure, I feel like I'm having a cold that's coming on. It's one of those colds that hits you like around 2 o'clock before you realize anything was wrong. When it comes to solving this quiz, you can do this in a lot of different ways. So for example, some people might just take out ordinary paper, open up this file here on your computer, and just start solving this in a traditional way. If you're that kind of person that's working on ordinary paper, all you have to do is either scan your work, or taking a cell phone picture of your work is totally fine as well. And send your work to my email address here, mikejacobson@isu.edu. Watch out for the EN. That's probably the easiest mistake to make. Once you send me your quiz, I'll automatically respond back to you saying thank you. That way you know that your quiz was received. So that's if you would like to work just on ordinary notebook paper or printer paper like this is. Some people might print these out and solve it on the paper as well. That works out just fine. Other people still might be using digital tools like I'm doing here. So you might download this to your computer, use a digital pen, and just write in your solution. If you're a person working with digital tools like that, just save this as a PDF or take a screenshot. And then once again, send it to my ISU email address. And that's how you'll submit each of your quizzes. You could submit these early if you like. The due date is fully a week away, just to give you a chance to ask questions if you have any on the quiz. So even though it's a quiz, I'm calling it a quiz so it's not called homework because we already have the Newton homework in that homework system. Even though it's called a quiz, it's really just a take-home quiz. It's kind of like a participation credit in the class. You're just doing a quick problem, sending it in to me. And it's also a way for you to practice on a problem on paper or with a digital tool, more similar to what they're going to really look like on an exam situation. So this is your opportunity to practice showing all your steps, showing your work, those kinds of things. And when I give you feedback, you're going to see what does a graded exam question really look like. So be sure to pay attention to your feedback, and it'll help you a lot in studying for your exams. Well, I think that's all I had to say about the quizzes. Any questions at all, folks, before we go to the next topic about quizzes? Okay, let me go back here. If you like, you can also find the quizzes on the assignment page right here. I typically find that most students are going to want to look to the bottom of each of these weeks. So that's where the quizzes are always going to be found. Well, aside from that, I think I'm out of announcements. Maybe one other additional announcement. Reminder that these are all video links, which are optional material, but really helpful for studying for not just this class, but other classes as well. And once we get into, let's see here, this week of September 22 to 28, so a few weeks away already, exam one is going to be held on Tuesday, September 23rd. As we get closer and closer to that exam date, we'll talk a little bit more on how to schedule your exams. I sent out everyone in the class just a quick questionnaire on which campus are you closer to. Some people are close to the Pocatello campus, some people closer to the Idaho Falls campus. Some people are far away, maybe around Meridian and so on. And so I'm soliciting feedback so that once we get closer, I'll be able to give you individually, student by student, the information you need to know to schedule your exam. Let's go back to where we were here. Well, any other questions so far before we begin working in section 2.7 where we left off? Okay, let's jump back in then. So section 2.7 is split into two parts. It could have been one overall huge section, but the homework is also split into two parts, so I thought it just makes sense to match it up as well. So we're solving algebraic expressions that involve the absolute value symbol. This is just the distance from the variable u to the number 0 on the real number line. And our fundamental technique is, if there's a positive number here where the red dot is currently, then we just split into two equations. U is equal to either negative a or it's equal to positive a. This is the problem that we left off. Shouldn't have scrolled that fast, sorry. This is the problem that we left off on. Now let's do another one of these just for the warm up as well. So here's part D. And occasionally on the notes, we'll just invent a new part if we feels like it's a good problem to do as a warm up before we start class. And this is one of those kind of problems. We're just going to make it up out of thin air. Here's part D. We're just going to pen it in. And we're not totally making up. I have a list of problems here. This one looks interesting. We'll solve 3 times the absolute value, 2x minus 5, close the absolute value, plus 5, equals 14. So that's our first problem of the day. The first step we want to take on this is isolate absolute value 2x minus 5. Wherever the absolute value portion is in your problem, we want to get that totally alone on one side of the equation or the other. We'll keep ours on the left-hand side. So I'm going to recopy this line just so we know what equation we started with before all the additional marks come in. For isolating absolute value 2x minus 5, think of this as just one big x itself. We want to eliminate the plus 5, then we want to eliminate the multiplication by 3. So start with subtract 5. Then we have 3 absolute value 2x minus 5, close absolute values, is now equal to positive 9. Then next step is divide by 3. We have absolute value 2x minus 5 is now equal to positive 3. And now here, use the property. If we have absolute value of u, we're just restating the formula, equals a. Then u equals negative a or u equals positive a. So it's critical we do it just at this step. If we did it at the very beginning, we would actually get the wrong answer. So being mindful of isolating the absolute value 2x minus 5 makes us more sure we're going to get to where we need to go more accurately. So this is the fun part. It splits into 2 equations. First equation is 2x minus 5. Seeing the formula on the right, we drop the absolute value And whatever is inside, we just directly copy it in, whatever it is. Right-hand side is going to change signs. It was positive 3, so now it's a negative 3. Or the next one is nice. You just copy the whole equation. You literally just drop the absolute value bars and nothing else happens. So here's the other equation. 2x minus 5 equals positive 3. So we've split into one equation with a negative sign and one equation with just the number directly copied in, maintaining its positive sign. So that's the critical key step so far. Now all we have to do is just solve both equations. So we're in the relaxing part of the problem. Sure, it is 2 equations, but nothing as overly complex as it was at the very beginning here. Any questions at the moment? Halfway through the solution? Okay, let's work our way through it. Going left to right, starting at where the red dot is, add 5 to both sides. 2x is now positive 2. Then divide by 2 on both sides. X is now 1, and halfway there. Just rinse and repeat. Add 5 to both sides on this one. Same steps, just different results. Now it's 2x equals 8. Divide by 2, divide by 2, and x equals 4. At this stage, we did it. We can celebrate. The equation has been defeated. The only way that this original equation up at the top is true is if this x right here is either a 1 or a positive 4. If you're left your work like this on a quiz or exam, it's totally acceptable. I can tell just by reading line by line what you're stating your solution is. In the homework, however, we usually state it this way. So x equals 1, 4. Newton is usually going to print the x equals part, and you're just putting in the solutions you found separated by a comma. So this is our solution set. We did it, folks. That's pretty much the main part of section 2.7. I have 2 additional problems I want to take a look at, a couple more that do show up in this section that are a little bit more tricky. But any questions or comments at the moment? Okay, well, we're off to the last 2 on these notes. And notice how different these look all of a sudden out of nowhere. Again, I don't think there's a lot of these in this particular section, but it's confusing when it comes up. So I have 2 examples of this type. This one, part A and part B. We'll start with the part A here. They're confusing to start because there's absolute values now on both sides of the equation, but really it's the same kind of process. We just have to be really mindful of parentheses. So the very first step we take is split into 2 inequalities like before. The first one is going to involve a negative sign, and that's where the parentheses become really critical. We drop absolute values on the left, so it's 9a plus 5 equals. On the right, let's look by just analogy what we did above here. We put in a negative sign when we went to that second equation, and that's really the solution to this one. Put in a negative sign. And this is the dangerous step already right here. We also have to include a negative, or excuse me, a parenthesis, sorry, talking's hard today, so that the negative can distribute on whatever was inside, 9a minus 1. So that deserves a comment already on its own. Do not forget, I have to pluralize this, these parentheses. And that's about the hardest part about this problem, remembering to be mindful about the parentheses. Parentheses. Then the next equation, let me drop it over here, is going to be same thing. We just drop both absolute value bars on the left-hand side and on the right-hand side. So 9a plus 5 equals 9a minus 1. So now we need to solve both equations. One on the left looks a little bit more technical because of the negative sign, but really the core step here that we want to take is just use the distributive law. That negative sign is really shorthand for a -1, and so -1 is going to multiply the 9 in the 9a and the -1 over here. So first let's copy 9a plus 5 is equal to, then distributive and negative. Another way you can say this is it's just going to flip both the signs. So this is a positive 9, it flips to a -9a. This is a -1, so this flips to a positive 1. Or again, a different way to think of this is really just literally -1 times 9, so -9, and then -1 times -1, a negative times a negative gives us that positive 1. Any questions to that step, folks? Navigating through the parenthesis and the distribution. Okay, it is a trickier equation even after doing that step. Both of them are trickier equations. This one has the variable 9a, or excuse me, said better, this one has the variable a and a on both sides of the equation. So usually all you want to do in this scenario is just add 9a to both sides. So let's go plus 9a plus 9a. Strategy here eliminates the fact that variables are both sides by just canceling it off on the right-hand side. So here on the left, it's now 18a plus 5 is equal to just a positive 1 now. And these are the equations we're a little bit better at. The ones we know and love, the same strategy still applies. Subtract off this number or add it if it was a -5, and then divide by whatever's here. So let's start by subtraction by 5. You could have done that all in one step if you prefer, and sometimes we might take that. But for the moment, not a bad idea while we're warming up, just to separate it into a couple steps. It's now 18a equals -4. Last thing now to do is just divide by 18. So divide by 18 here and here. Left-hand side is nice. Now a is all isolated on the left. The right-hand side is a bit problematic. If you wrote -4/18, you could get partial credit on this on quizzes or exams. But the reminder on this one is we must reduce all fractions. And we want the exact value in fraction form. That's typically what the Newton system is going to ask for. So let's just divide by 2 into the numerator, divide by 2 into the denominator. Don't forget the negative sign, that's an easy mistake to make. And we have left over -2/9. So that's part of the answer. Now all we have to do is see if there's anything extra by solving the other equation. Again, it's a lot of work. These absolute value equations just are really two problems duct taped together that we split apart in this kind of way. Now, if you've been eyeballing this one, it is definitely weird. So if you've noticed something odd about it, good on you. This one was an equation we could solve to get a number out, because when we added 9a to both sides, we got a still surviving, 18a. But now on this one, no matter what we try, however we approach it, we're eventually going to have to get a on one side of the equation or the other, but that's going to force a to be eliminated from the whole equation. So for example, if we take -9a, -9a, then a is gone on the left-hand side, it's just +5. A is gone on the right-hand side, we just get -1. And now we're in this really awkward position where the original equation led us to a statement that 5 equals -1. This is completely false. Or you could say it's a contradiction. So this means the equation that we put down here, even though it was the correct algebraic step to take, It had no solution. But we're only talking about this one part. So if we want to be really specific, this is the solution. And putting a box on it probably wouldn't hurt in this context either. The no solution is again just referring to this one equation up here. So probably you want to write it kind of small, just so it's contained into that one side of the work, emphasizing that this is the solution that you would answer the question to. Well, we did, folks. That's a trickier one. We'll do one more just for the practice. Any questions on how these steps work so far?
Actually, I have one question. So at the start, it's hard to go back pretty far, but how come you chose to do 9a plus 5 and then put the parentheses around the second one? Could you flip that, or would it still not work? Would it work the same if I did 9a minus 1 and then did the parentheses over the 9a plus 5? Why not? Does it make sense? Sorry.
Oh, put the C say on this one you're saying?
Uh-huh. And then the 9a minus 1, we would
Yeah,
equal to that. Would that equal the same thing?
it would, but the only change you would have to make is the negative would have had to have been on the other side as well if you went on that route.
Okay. That's my question. Thanks.
Yep, absolutely. So yeah, it turns out it doesn't matter which side you put the negative on. As long as it's on one side or the other, you're all set and you'll get the same answer. Thanks for that question. Other questions at the moment? Okay, let's maybe pause on this one a little bit more and do one of those rare things that you might have been thinking about, but we really haven't done too much so far in this class. Maybe we haven't even done it a single time. Let's imagine you're in a scenario where you're taking an exam, you completely finished off exam one, and this is one of those problems, and you're thinking, well, I finished my exam early. I still have 10 minutes of time left over. By the way, that's how I try to write the exam so that the average well prepared student has extra time at the end, not that you're writing the whole entire time. I try to give you time to check your work. You might decide with the extra time you have to check this. Maybe you made a mistake. It is a weird kind of problem, right? So let's check our answer. It is sometimes a lot of work to do a check. So when you're solving an exam, I would say solve each problem. Then with the additional time that you have left over, then go back, look at problems that you feel maybe a check is worthy on, and do it off to the margin. And even if things don't work out in the check, leave everything here as is until you spot the error and fix it. One mistake that also happens is sometimes people erase the whole thing because they detected something wrong, but then never filled in any additional work. Even if there's a mistake here, I grade on partial credit. So for example, if I just messed this up right here and put in a positive 4, and this was a 5-point problem, you would have gotten 4 out of 5 points. That would have just been a simple mistake. But let's give this a try. To do the check, we take the -2/9 that we found for A, we're going to plug it here and here into the very, very original equation. Not where we split it up here or here, but at the very, very top. So go absolute value, maybe a little bit taller this time, 9 times. Here's where I'm putting in A, which is a -2/9. Good practice with arithmetic as well. There's lots of side computations to do here. Then 9 times, -2/9 again right here, then -1. So now we have to do some extra simplifying work. The nines cancel out, so that tells us maybe we are on the right track. This is kind of nice in a way. Cancels out on both sides there. We have to be really careful with order of operations, so we're working inside, do the multiplication first, then the -2 plus 5. But let's work this out step by step. Here, this one just reduces to -2 minus 1. Now, if you're really curious if this is going to work out, we're getting closer and closer to checking. On the very left, still order of operations, we have to do -2 plus 5. Then and only then can we do the absolute value. It'll be absolute value of a +3. On the right-hand side, -2 minus 1 will give us a -3. And now that we've done that, we can do the absolute value on the right-hand side. So what is absolute value again? Recall it's just the distance from 3, if we're looking at this side, to 0 on the number line. That's just 3 itself. The distance from -3 to 0 on the number line is also 3. Or sometimes people visualize it as if it's just a number, no operations, forcing us to do order of operations. If it's just a number, whatever is inside absolute value is forced positive. So that would turn out to a +3, and we get a true. That tells us the check was successful, so let's just put a check there to emphasize. And then you could have extra confidence on your exam that when you hand it in, you were right on this one. I mean, in the very, very, very rare circumstances, you might have made an error here and then an error here, and it just looked true with the 2 errors. But that would be very, very exceedingly excruciatingly rare for that to happen. Well, any questions, folks, on the check side of this equation here? Okay, well, let's do one more problem of this kind, and then we'll move on to the next section, 2.7, part 2. This deserves a new page. These are kind of longer problems than they would seem at the very start. Same as the one as before, it's absolute values on both sides. And if we didn't practice these problems on the notes here, this would have been a pretty confusing homework on the problem on the homework, I would say. So that's the purpose of doing that. My arrow disappeared. What is going on? That is weird. Let me try again. Okay, it didn't disappear this time. So the first thing we do is be really, really excruciatingly careful with using parentheses where we put our negative. Based on the question as before, you could put a parentheses on 8x plus 6, then a negative goes in front of that one as well. And I usually, just as a process, only put it on the right-hand side. So this would be 8x plus 6 equals, here's the negative sign, and here's the trickiest part of the whole problem, those parentheses right there in purple, or violet, whatever color this is. Turns out this color is plum. I don't know if you can read that text, it's kind of small. Then next equation is 8x plus 6. Let's put an or between. Not strictly required, but just a way to convey two conditions, this one or this one. 8x plus 6 equals x plus 1. So here, directly copied, just drop all absolute value bars, and we're all set to begin with this one. Let's go left to right. The right-hand side is the trickier one because it requires a couple extra steps. Well, one extra step with the distributive law. This will be 8x plus 6 equals. I'm a fan of arrows, so usually I visualize the distributive law this way. This will be helpful when we're FOILing polynomials and that kind of stuff. So that'll be negative x. Distributing here to here will give us a -1. And now we can take the same similar kind of steps. You always want to get x just on one side. If it's smeared across one side and the other side, that's not helpful for us. Easiest thing to do is just add x to both sides. And if you're the kind of person that might want to take another step at the same time, you know, it couldn't hurt. You could subtract 6 here and here as well. But this problem is big enough. Let's just go step by step on this one. So we're not doing too many steps all at once. 9x plus 6 is now equal to -1. Now I would subtract the 6 from both sides. We have here a cancellation where the red dot is, and just 9x equals -7. Finally, division by 9. At this stage, x is equal to -7/9. One part down, we just are going to go off to the next and solve from there. Any questions, folks, with these steps so far? Okay. Kind of the fun thing about these is it's very similar looking steps, except you might notice a pattern. If you added x on this one, due to that changed sign, you're going to do something different. This one requires that we subtract x from both sides. So subtract x from here to here. Very similar process, just slightly different numbers. In this column, these are like terms. 8x minus x will give us 7x's plus 6. And on the right, it's a cancellation, just a 1. Now this time, same exact step. Subtract 6 from both sides. 7x is now equal to -5. Slightly different step now. We're dividing by 7. But very, very similar in spirit. And x is now equal to -5/7. I'll put an or between the two. So now we're saying x is -7/9 or -5/7. Well, that was the last one for the notes. Any questions or comments at all, folks, before we close out this section? Okay, we did it. This one's a pretty tricky section, but it also leads into the next one, section 2.7, part 2. And we get a nice graph that goes along with this. So we've been dealing a lot with absolute value, inequalities, and the next section kind of fits in with the next section, part 2. Last section was absolute value equations, and now it's inequalities. And this is a graph that I lifted right out of our textbook. So it's kind of nice. This was the prior section we just looked into, part 1. The next 2 rows, this one and this one, this is what part 2 is all about. And there's a lot going on in this chart. So my thought is, as we study this right here, we'll do our own chart running through this example 1. Well, what's going on? It says let any a be a real number, any real number that is positive. If that's the case, this right here is just the formula from our very last section, 2.7 part 1. Absolute value of x equals a means x is either -a or positive a. And this is what it would look like on a graph. Just 2 solid points. The solid dots is a better way to say, is just a way to say these are the only 2 numbers on the solution set. Now here's where it gets a little bit trickier. Now it's the absolute value inequality. If the absolute value of x is greater than a, it splits into a compound inequality. This is now section 2.6, where x is less than -a, or x is bigger than a. In our textbook, they used a parenthesis on the graph, but to more match with what the homework is going to look like, let's put an edit on this one. We'd really see it as an open dot here and an open dot there, so the way we would typically enter in our answer. Then, now absolute value of x less than a, this one becomes a triple-sided, so 3 different sides, the left side, a middle, and a right-hand side. So now a triple-sided inequality. Again, that's another problem we practiced in section 2.6 as well. And on the number line, let's put in those open circles as well for emphasis. This is what it would look like. And you know, this probably deserves some good explanation. This is a really tricky kind of problem in a certain sense. Your question might be, why? Why is it that a greater than a splits into 2 regions that just go away from each other? And why is it that when it's less than a, it's just one solid region contained in this way? Well, best way to see that is put in the 0. So I already have a couple changes to the textbook's graph. Keep in mind our textbook is free, so it's not meant to be perfect. It's a big money saver. Occasionally, this is one of those graphs from the textbook that I felt like could have used just a little bit more detail to convey what we really want to say. So here's one additional comment. Recall, absolute value of x equals the distance from x to 0 on the number line. So this is the really big explanation of why do these three solution sets look so radically different out of nowhere? So on the very first one, absolute value x equals a, we're saying it's only 2 points because these are the only 2 points whose distance away from zero is exactly a. And we'll reduplicate those comments and actually write them out on our example below. But just to give you an overall idea of this one, let's look at row 2 next. It's a greater than a. So now it's saying the distance from x to 0 on the number line is larger than a. So that's why it's not here. That distance is a itself. It has to go either way out here. Now it's far away from 0. Or way out here. Now it's far away from 0 as well. So in other words, x is far away from 0 by a distance of a. So that's why they're repelled away in this kind of way. Last, and equally important, this one is saying the absolute value of x is, or let me say it better, using the distance from x to 0, forgot about my way of thinking. This is saying that x is close to 0. It's close in the sense that it's within a. So this is verbatim saying the distance from x to 0 on our number line is less than a. So 0 is less than a distance away from itself. That's why it's inside here. It's a solution. And everything's small. Small so that it doesn't go beyond a is a solution. So that's why they're all kind of constrained in this region, right where the red dot is. That's a lot of thoughts to keep in your head all at once. So example 1 is us redoing this with specific numbers. Also, the graph that they gave in the book had strictly less than, strictly greater than. They didn't show greater than or equal to a. Maybe they were saving on pages on their digital book. It's kind of a weird thought. So I mixed up mine. Mine has a less than or equals to, and then a strictly greater than, just for a little bit more variety. So let's scroll down to this part, and we're just going to do it all over again for actual numbers instead of a variable a. Any questions or comments first before we launch into this example? Okay, I want to kind of go in the order that these were shown. So let's start with absolute value x equals 3. And by the way, in the notes, I changed this so that the less than equals, oh no, I didn't. I must have forgotten actually. I want to change this one just a bit and make it a, well, you know what, we might as well leave it the same on paper. I'll just go to this one second. So that's in the same order as this one. So starting on this one, it's absolute value x equals 3. We're going to compare the solution sets of all three of these expressions, express the solution sets in the forms of graphs and in interval notation. So this one was just the last section, 2.7 part 1. When we write this out as a graph, it looks like this. First, I want to plug in 0. The absolute value of x equals 3 immediately implies x equals -3. Let's write it out in the same way, or x equals +3. So here's the -3 portion. Here's the +3 portion. It's said to express the solution sets in interval notation, but this is the one time interval notation doesn't apply because these are just two discrete points. There's no interval of points whatsoever. So I'll just say briefly, interval notation does not apply. So this is the one time we get out of it. So the reason these two are solutions, just as a reminder, is this is saying distance from x to 0 is exactly 3, or I'll just say equal to 3. Well, one down, this is kind of just duplicating what we saw in the notes in the very last section. But because these all kind of go together, this is more a compare and contrast kind of problem, seeing how this inequality is going to fit in with the inequalities here and here. So now we're going to do row 2, where it's the greater than. So I'm going to grab this one out of order. Sorry, that's kind of jarring. Do absolute value of x is greater than 3. Now let's start with the comment. This is saying distance from x to 0 is now greater than 3. This greater than has an impact. It means x is far away from 0. What's far away? More than a distance 3. So let's rewrite the number line on this one and try to keep them as similar in scale as possible. 0, I'll try to keep in the same location. -3 is just as important on this one, and so is +3. We're going to use an open circle because of the strict equality here. Excuse me, strict inequality, said that backwards. Then blame that on the cold. Then we shade in this direction. This is far away from 0, more than a distance 3 if we're out here. And so is all of these numbers. Every single number bigger than 3, excluding 3 itself. So it goes off to -infinity, +infinity. If we were to write that out in interval notation, this would be -infinity up to -3. We use the union symbol again, so this makes a comeback from section 2.6. And then from 3 to +infinity. So that's the graph, that's the interval notation. But you know what the really critical part about all of this information is? How we go from this to this. This is actually the biggest part of the discussion. That formula in the purple, I guess this color is plum. That formula in the plum box is the biggest thing about all of this. If there is a greater than sign, notice this only happens for the greater than sign. When that happens, we take and rewrite x less than -3 or x greater than +3. So this is the fundamental formula that we're going to come back to. Doesn't seem like as a big of a deal if it's just absolute value of x, but hold that thought. It's going to be more involved, like 7 minus x, x plus 1, x 8 minus x, and so on. So this becomes a very important formula when the problems get bigger and bigger, like the ones we just peeked at. And this strip right here is just the statement x less than -3. This is just the statement x is bigger than +3. So that's another way to visualize what's being expressed in our textbook from this row. Now we'll do it all over again on the third row. But any questions at the moment, folks, with what we said over here? I want to put in some highlighting because since this is the trickiest part of absolute value inequalities. Okay, let's finally do is less than a version. So that would be absolute value of x is less than or equal to +3. We have written there. So let me copy this one in. Absolute value of x less than or equals to +3. First, let's think conceptually, what is absolute value? What is this whole thing trying to say? What this whole inequality is expressing is that the distance from x to 0 is less than or equal to 3. Now, you know, we already did the or equal to right over here. You just put in those solid dots. So that's going to be part of our graph when we go to write it in. So just as this was distance was greater than, this is a distance being less than 3. So all the numbers are close to 0. How close? Within 3 in distance. So let's write out our third number line. I'm trying to keep these 3's all lined up to the best of my ability doing this freehand. Here's -3, here's 0, here's +3. And this really is a compound statement. X is less than 3 or is equal to 3. But we're equal to 3 has already been handled. We just put in a solid dot here and here. But you're probably expecting that, right? We already discussed in section 2.5, less than or equals to always becomes a solid dot on the graph. That's just a way of saying these boundary points are part of the solution. Open circle is a way of saying these boundary parts are not a part of the solution at all. Then the last thing is, if the distance is small, or if x is really close to 0, since the distance between x and 0 is less than 3, then the solutions are in the middle now. If I grabbed a number here like -4, absolute value of -4 is +4. +4 is not less than or equal to 3 whatsoever. And so that's why the solutions are now in the middle this time. So we would shade this way. Then go into interval notation. This would be, we have to be careful. We've used a lot of parentheses on the last one, but this time it's a bracket. Bracket -3 sets it's inside the solution and go all the way up to through the interval, +3, and close the bracket on that end. So those are all the numbers that solve this inequality here. There's more to the story, but any questions at the moment? Okay, like we made a big deal out of on the books graphics right here, this is the major part. So let's do that emphasis again. If you ever see a less than or equals to, either version is going to give you the same result. You go to the triple-sided inequality right over here. In practice, this is like the most important part because it tells us algebraically, what is your next step? How do you actually get to interval notation down here, our ultimate goal? So when it says absolute value of x is less than or equal to 3, whatever x is, we'll rewrite this as, take this, change its sign, now -3. Less than or equals to is just going to copy whatever is here. So if it was strictly less than, we've gone less than as well, like up here in the formula. Put now x in the middle, less than or equals to +3. So highlighted in yellow here are the major parts to watch out for. It'll be negative on the left, positive on the right. I'm tempted to highlight the whole thing, but then the highlighter becomes less worthy if you're just highlighting everything. But those are the two things that we would have to get to the right solution set. So the short story is greater than means you flip this to a less than. That's actually easy to miss on its own. Put in a negative sign. And then on the second inequality, copy everything down just pretty much verbatim without absolute values. So greater than splits in that way. If it's a less than, or a less than or equals like we see by the red dot, you go negative, then positive, whatever the number is, x is in the middle. Kind of makes sense. It's in the middle right here, for example. Well, this is our big rundown of how to get through these problems. When you're doing the homework in section 2.7 part 2, use this as kind of a guide. If you like the graphics above, you might be just fine with this information. It's a little bit more compact, which is helpful. If you are more curious about the why are the formulas working in these really weird ways, totally unexpected possibly, the second example 1 below is just telling us the why. So use these as a resource to help out with the homework. In fact, we'll cite this information here as we go to solve the next problems to help us out. Well, we're going to try out example 2, more similar problems to the actual homework set. But any additional questions or comments before we get started? Okay, let's give them a try. So first one is a less than. That's kind of nice. We can just scroll to about right here and look at the formula right above. These instructions probably feel similar to section 2.6 and 2.5. It says solve the inequality, express the solution sets in the form of a graph. We were using blue for our graph, so we'll just keep on doing that. And in interval notation. So that's our goal. And much like in the very last section, there's often a very first step you want to take. If absolute value has anything around it, like a +3, or if it has like a ×7 and then a -3, step one is just to immediately isolate absolute value. So let's just make that an important comment. First, isolate the absolute value. Not two different steps from what we've seen. First thing we'll do is subtract 3 from both sides. If we do that, we'll have 7 minus x, absolute value, less than 5. So 3 cancels, 8 minus 5, 8 minus 3 gives us that 5. Now we're ready to get started already at this stage. Observe that if it's a less than 5, then we get the following. First thing we do is write, without the absolute value bar, 7 minus x. Oh, let me put that in the middle. 7 minus x. Then it's going to be sandwiched to two inequalities, less than, less than. So here they are. Less than, less than. The far left side of this triple-sided inequality is going to have the opposite of 5, so -5. Might as well keep the same color coding here. -5. And the far right-hand side will just have a +5. So same steps as we illustrated above here. Sometimes it looks a lot different when we go to do it in an actual problem. So here's what that very first step looked like. Maintaining highlighting and color coding and all the rest. Once we're to this stage, we're pretty much home free. We just have to solve what we have here. This is where section 2.6 on the compound inequalities starts to take over. So to simplify all this, we want to keep x in the middle, that turns out, for this one. So let's take the first step of just subtracting 7 from both sides. I said both sides, but that's not accurate. We want to say subtract 7 from all 3 sides, the left side, the middle, and the right-hand side. In other words, it doesn't matter that it's a triple-sided inequality. Wouldn't matter if there's 10 sides to this. Whatever you do to any side whatsoever, just do it to all the rest of the sides, and it's the same algebra as before. So take a tally. On the left-hand side, -5 minus 7 is going to take us down to -12. We didn't multiply or divide, so inequality is in the same direction. Cancellation here, just a -x left over. Less than 5 minus 7 will take us to a -2. Almost there, except x is not isolated. There's a negative sign there. Now we do have to be really critical and mindful of division by a -1. So I'll write in a new row, -12. We're dividing by -1 here. -x we divide by -1. -2 divide by -1. But now that means all inequalities this time are going to flip. Less than is a greater than here. Less than turns into a greater than here. Now let's just simplify what we've got. We have that 12. It's greater than x, which is greater than 2. That's a great inequality, but just like we commented on the prior sections, if it's helpful for your mind to visualize this going into the graph, you might want to change the order of things so you can flip even a triple-sided inequality. Before we flip it around, any questions at all, folks, to this point? Okay, let me rewrite it as 2 less than x less than 12. So if you flip everything around, you're also flipping the inequality sign just one last time. Just make sure again as a check, if it's pointing towards 2 over here, it should be pointing towards 2 over here, the point of the inequality sign. Likewise, it was pointing towards x over here, and it's pointing towards x over here. So if you have that consistency, you're in great shape. So this is the solution set in inequality form. But we also wanted the graph. So here's the graph. There's two key cut points, 2 and 12. So cut the number line here at 2, cut it again at 12. We'll require an open circle for this one to match the less than sign, and shade in the middle. Finally, once we have that, really the purpose of doing the graph each time is just to help us to get that interval notation down pat. We just copy what we see above, going parenthesis for the open circle, 2, comma, 12, and then another parenthesis for that open circle. At this stage, we did it, folks. These are pretty challenging problems when you're seeing them from the very first time, but that's one down. Any other questions so far, finalizing this one? Okay, let's try out another next one to see how we'll do. This one has a greater than sign. Let's put it on a new page. Sometimes I write pretty big, so I need to move things around. And you're probably looking at the notes that you wrote down from the first page. Let me grab it here as a screenshot. It was a greater than version, so I want this information here. The moment the screenshot goes, there it is. Uh-oh, didn't want to do that. Control Z to the rescue. Okay, occasionally we'll make some liberal uses of screenshots anytime you have to cite a formula. So now we have a greater than direction. We need to be really, really careful when we go to split this up. The same first step as always. Absolute value x plus 1 needs to be all alone. So first preliminary steps, let's add 3 to both sides. So 7 times absolute value x plus 1 is now greater than 14. That's a nice number to go with 7 on the left. Now divide by 7. And we have absolute value x plus 1 is greater than 2. So now this is the critical step. These are really hard to nail down unless we get these steps just right. It's saying now x plus 1 is greater than 2 in distance. This formula said just x, but it could have been anything whatsoever. So whatever is inside the absolute value bars, we'll take it and split into this new compound statement. Because it's greater than 2, this is the only reason, it's going to converge into this one, not the triple-sided inequality at all. We're going to get x plus 1 is this inequality sign flips on us. It's now less than. 2 flips, it's now a negative 2, flips in sign. Or go back to the x plus 1 here. And this time, this one's the friendly equation. Comparing it to the original up here, all we do is drop the absolute value bars and copy it in. So absolute value x plus 1, take off absolute value bars and just say greater than 2. Let's highlight these again just to get some parallelism going. This is a tricky problem. So once we get through that key step, we took something challenging, section 2.7, and now it's a section 2.6 type problem, a compound inequality. Really, that was the major reason we did section 2.6, so we weren't doing a whole bunch of new things all at once. Any questions, folks, getting to this stage here? getting through that critical step. Okay, well, all we now need to do is isolate x on both sides of both of these inequalities. And not a lot of algebra to do. We'll subtract 1 from this side. Subtracting 1 from both sides here is going to give us x less than -3. I don't like my penmanship there. Let me fix that. X less than -3. Subtracting 1 from both sides here is going to give us x greater than 1. Now we're home free. That's something we can plot really nicely. We want the graph and then the interval notation. Starting on the graph, here's what it would look like. 2 cut points once again. One at -3, one at +1. It's another strict inequality, so we'll use open circles here. It didn't say less than or equals to, in other words, just strictly less than -3. And this is a pretty good review topic just really all on its own. If you say x is less than -3, just means shade to the left. But you notice the way we kind of wrote this down sort of just lines up. It's right above where the solution set is on the graph as well. So sometimes organization really just helps you out and makes the cognitive load of trying to memorize everything all at once a lot more manageable. So this one says x is greater than 1. So we'll just shade to the right going this way. Off to positive infinity. There's an or symbol in the middle, which means there's going to be a union sign when we go to right interval notation. So that's making it come back again on these notes. Then just do the normal thing. A negative infinity always gets associated with the parenthesis. This set goes up to -3 with a new parenthesis. Parenthesis once again due to the open dot. Starting at 1, go off to the right. This is now saying all solutions larger than 1, but excluding 1 due to parenthesis, solves the original inequality way up here. So we did it, folks. That's our interval notation below, the graph above, and a tough inequality. Really, this whole step right here is the key step. So if you practice realizing that a greater than splits into the or statement, flipping the sign to a -2, you've gotten through the tricky part of this problem here. Well, any questions, folks, for this second tough problem? Okay, well, it looks like we have time to do one more, and looks like there's one more on the note, so let's give it a try. Looks like we won't make too big segue into the next section, section 3.1, but we'll probably open it for the last part of class just to take a look at what's going on there. We'll see how much time we have, if that makes sense. So now, same kind of deal. This is an absolute value inequality due to those two parts right there. And lots of stuff kind of going on. You know, even though it says greater than or equals to, you want to kind of look before you leap. Doesn't mean greater than or equals to is the big part of this problem. There's a negative sign right there that could change things, in other words. So let's do those usual preliminary steps. What we really want to do first of all is get this absolute value portion isolated on one side. Start off by subtracting 2 from both sides. It's now -4 multiplying 8 minus x in absolute value. It's greater than or equal to -14 minus 2, so -16. And now here's another opportunity to watch out for that danger. We need to divide by -4. So the inequality sign is going to flip. So this is possibly a different type of problem that we may have realized. Let me rewrite it just for emphasis on this step. So divide by -4 on the left. Divide by -4 on the right. the absolute instant that division occurs, where the red dot here, we get a change in the inequality. It's now a less than or equals to. This completely cancels on the left-hand side, so absolute value 8 minus x is now less than or equals to. Negative signs cancel off, 4 goes into 16 4 times. So this is the real absolute value inequality that we want to solve. We'll spin up to the notes to get the right part of this formula, just so that we can all visualize this better. It's a less than, so we're saying distance of 8 minus x to 0 is small. So we should expect just a small blob for our graph and interval notation. The key formula is, scrolling all the way up, this one right here. Okay, now we're ready to start in earnest on this one. So just to add some parallelism, let's do the same kind of arrow here. Once you get here, only because it said less than or equals to 4, it's the less than that's important, this splits into this new thing. We'll go -4 here, less than 8 minus x, less than +4. Really, the only thing different about the formula where the red dot is versus the problem we're just doing is this had only x, ours has 8 minus x, but really doesn't matter what's inside here. Anything goes. Whatever is where the red dot is, place it in the middle, and you're doing the right algebra. So another triple-sided inequality to handle on this one. Lots going on with it. We also have the negative x to contend with, so we'll maneuver through that as well. But here's the steps we took from like before. Subtract 8 and 8 from all sides. Oh, and I do want to highlight this in yellow just for emphasis like from before, and as well up in the formula. When we tally this up, we're going to get -12 less than -x less than -4. Next key step, we're just going to divide all sides by -1. So let me rewrite it just for the sake of clarity on that step. Divide by -1 here, here, and here. So now all signs change their directionality to greater thans. Scrolling a little bit more, running out of space on this one. We now have, let me move it off to the side so I don't just paint myself into a corner. 12 greater than +x greater than 4. And once again, if you're comfortable working with it in this form, totally fine. I just find most people, and I'm one of them, find it easier to have it just flipped around where the smaller number is here and the larger number is there. So this is a totally optional step. I'll write this as 4 less than x less than 12. At this stage, we're just about home free. We're just going to go through the methodical steps of write down the graph, write down the interval notation. Really, where all the purple arrows and highlighting is, that's the critical step on this problem. But any questions so far at any stage? Okay, well, we're just about done with all of our work on inequalities, compound inequalities, absolute values, and all of that. After we finish off these notes, we're going to now be in chapter 3, and the goal is going to be graphing linear equations. You might recall things like y equals mx plus b and so on. So this is going to be a kind of big transition into the next section. First, let's finish off this graph. I'm looking down either on this line or this line would be appropriate. The two cut points are going to be 4 and 12. These are solid dots this time because, oh wow, I made an interesting mistake on this. This is kind of one of those fun mistakes where it's easy to happen to anyone. This is one of the mistakes I personally make a lot. It was less than or equals to, and you might have noticed something fell apart when I went down to this step. I just forgot that it's also less than or equals to here, 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 and here. It's kind of unfortunate when you make a mistake towards the near top of a solution because the corrections cascade all the way down. I'll put them in red for emphasis. Greater than or equal to here, here, less than or equals to here and here. Okay, now we got it. Now with that correction, we'll have a solid dot because that was meant to be a less than or equals to x. Solid dots here and likewise here. We're just saying x is between 4 and 12. Or said differently, x is greater than 4, but less than 12. Either way you say it or visualize it, it's just all of this stuff right in the middle here. From 4 to 12, including 4 and 12. So that means down in interval notation, it'll be from 4 with a bracket to include it, all the way up to 12, but ending with a bracket to also include 12. And we did it, folks. That's finally our solution on this one. Well, any last questions at all, folks? Finishing off these section 2.7 notes? Okay, thanks for your patience today. I have a cold that's making my head just a little bit more foggier than normal. Probably my voice might be starting to sound a little bit weird. And we didn't get as quite as far as I thought I would, but you know, when you're managing a cold, you probably don't want to try to even think about going faster than normal. So I think I just intentionally went a little bit slower today. So not to mix up myself or anyone in the class. Last thing I want to remind you is don't forget about this quiz. It'll be due next Thursday. And also everything on the Canvas page is pretty dynamic. I put these things in the section where we're looking at them in the current week, but once we move and come back to next week, things move around in this kind of way. I leave these sections in the week that we're actually going to finish them off. So if you come back to the Canvas and things look different, it's only for that reason. Also, just a reminder, I re-upload these things that are blank right here with the solutions that we just solved. So these are great resources to help out when you're doing your homework. You can use them as reference problems now, or look into the textbook reference problems on their examples, or even the YouTube videos if you'd like. But any last questions at all, folks, before we call it a night? Okay, well, have a great evening, everyone. We'll be back at it on Tuesday in a brand new chapter. Have a great weekend.